Thank you very much. Morning, everybody. Sorry, I'm a bit late. Okay, good. Let's continue our discussion from last time. Try to wrap up the material on the multicast. We started looking at the intradomain cast routing, intradomain multicast routing. Intradomain means that's good. It allows me to catch my breath. Thank you very much. Good morning, everybody. Let's continue our discussion from last time. We started looking at inter-domain multicast routing. And again, as I told you last time, multicast routing, the purpose is to create a distribution tree, is to create the multicast tree that will forward the routers along this tree, multicast packets, only to those interested in receiving these multicasts. Several protocols. The first one is what is referred to as multicast distance vector. We call it DBMRP. DBMRP stands for the distance vector multicast routing protocol. It says that this one is also based on what? On the unicast distance vector. The unicast distance vector. The other type is called these, by the way, are the algorithms that might be used in here. This multicast link state. The multicast link state, which we refer to as what? As MOSPF. F stands for the multicast open shortest path first. And of course, this one is base cast, which is what? OSPF. OSPF. So for every what? For every unicast route, they build on what? They build on top of it what? A multicast routing protocol. Keep in mind, tables. In other words, the multicast table and the routing table, the unicast routing table are separate. Clear? But they are laying on top of each other, laying on top of each other. And then the one that is most widely used, known as the protocol independent multicast. Protocol independent multicast, this is what is referred to as what? Protocol independent multicast. This is a routing protocol that is independent on which protocol you are using. In other words, it works with all unicast routing protocol, whether it's what? Link state. This one is classified into two types. The first one is called PIM, stands for Protocol Independent Multicast, the dense mode. And all the what? Most of the routers that are involved in the multicast, most of the routers that are involved in the are located what? Close to each other. Close to each other. That's what is dense mode. Dense mode means what? They are located near each other. Whereas the sparse mode, routers that are involved in the multicast tree are located what? All over the place. They are not located with what? Located here, the other one is located there, the other one is located here, and so on and so on. We call it what? Sparse is what? It is located in a sparse fashion. And we will see the difference between each one. Now, the multicast group, the multicast protocol can be classified into whether base tree or whether they use what? A group share tree. Remember, in a source-based tree that we talked about, in a source-based tree, every source will create a what? Sorry, there will be a multicast tree for every source. We do have n sources. We need to create how many trees? N trees, one for each source. Where the tree, we are going to use only what? We are going to use only one tree to share among all members of the multicast. Again, the one that depends on the source-based tree is the MOSPF, the DBMRP, the PIM is also source-based tree. The beauty of this one is the one that is most widely used. The beauty of this one starts with a what? With a shared tree, Start with a shared tree, but if it discovers that there is a more optimal tree, that source, it can switch to that. Which I'll show you in just a second. That is the one that is the dominant one. The dominant one currently in use is PIMSIM. PIMSIM, again, is the protocol independent multicast sparse mode. And again, as I told you last time, at USC some time ago in the early 80s. Clear? It was developed at USC department. Unfortunately, the professor who developed it left us. She went to UCLA, to the enemy. She joined the enemy. Okay, which is terrible. Okay, this one we already, the reverse path multicasting, reverse, and the core base tree. Did we talk about this last time or not? Quickly review. Did we talk about this? Remind me. Did we talk about this? Now remember, in the reverse path multicasting, one here, in the reverse path multicasting, what is another name for it? Another name for it is what? Flood and prone. Quickly, let's review it. In a flood and prone, when a router, remember, it's a source-based. It's a source-based. So let's assume this is the source. When a router receives a packet, if the parent port, what does it do? It will what? Send it to all what? Send it to all child ports. Okay, so for example, in here, this one here is sending here, is sending here. Now this one here, this one, at the beginning, it will also send it here. This one will, but if there is no interest in here, what does this one send back? He sent back what is known as a prone message. What? This router is telling this router, don't make copy for me. Don't make copy for me. I have no interest group. So this one now is what? Is a prone from the tree. So he sent it to here. Now, will this one make a copy to here? This one will make a copy to here. Why? Because there is an interest in here. This one will. Why? Because there is a what? There is a interest in here. Now, answer me the following question. Why is this one not sending it to here? Why is this one not sending it to here? See this one here? In this group, this interested group is connected to two. This router is the one that is closest to the what? To the source. Closer to the source. So when this one knows that the shortest distance from here to here is through this one. So this one is behaving as a what? As a child. You receive something on a child port, you will not what? You will not forward it. So the packet will come in here. So in the reverse path multicasting, which is the one that is dominant one to be used for source-based tree, at the beginning, packets, you send it what? Flood, and then wait for what? To see responses from other routers. Are not interested, they will send you what? Proning messages. And remember, every router, a prone message to an upstream router, he must have received what? A proning message from all ports. From all his child ports. If he receives a prone message, then he can forward the prone message to the upstream router, telling him what? Don't send me any what? Don't send me any multicast. Clear? Okay. The core-based tree, again, we did this one last time. In a core-based tree, what do we have? That is designated as a what? As a core point or a rendezvous point. Let's assume this is R5. Here, R1, there is a source at R1. Remember, this is not a source-based. All of them will share the same tree. Will unicast, not multicast, unicast a join message. To who? To this R5, to the core. Which means what? Tell me this packet that this one is sending. What address? What is the source IP address in this join message? The source IP address in this join message. What is the destination IP address? R5. It's a unicast. It's not a multicast. Telling one to join this multicast group. Notice here 3, the designation is like this. What is this? One more time. What is this? This is wild symbol. What does it mean? It means that I don't care about source. I only care about what? Which group is it? Do you follow me? Why? Because all of them are going to share the same group. Sorry, they share the same tree. They are sharing the same tree. So this one will send a join message. When R3, next hop router, R3, when R3 receives this join message, what he will configure this port to be part of what? To be part of the tree. He will remember that it receives a join message for this group on this interface. What? This one becomes part of the tree. Now what will this one do? He will what? He will forward it. Who is the next hop router? Who is the next hop router? R6. R6 again will remember that it receives from this interface. This also becomes part of the branch. This one then what? For the same packet. This is the same packet. The join packet. He sent it to the the rendezvous point again will remember that it receives a join message on this one. Clear? There's another group member. Let's assume that there is a group member here attached to R3. And this group also wants to join. When he sends a join message, this router does not relay it to. Why? Because he already remembered that he did earlier that thing. Did you understand? Already did this. This is already a part of the branch. Sorry, this branch is already a part of the tree, so he doesn't send it again. Now, this one wants to send a join message. He will send a join message to the what? To the core point. Again, this is a unicast message. This becomes part of the tree. Now, where is the overall tree? This is the overall. All of them will use this tree. All of them will use. Clear? Okay. The problem, again, as I told you, the problem with the core-based tree or with the share, it may result in the concentration of the traffic. Most of the traffic will be concentrated to the what? Around the core. Everybody is sending what? Join message. The beauty of this one, it does not have any flooding. There was no flooding involved. Are you following? Only if you want to join, you will send a what? Message. There is no flooding in there. In the previous one, the source base, there is always what? Flooding in there and then wait to what? Which is to be pruned. Clear? And here there is no flooding. You want to join, you send a join message to the core point. Clear? The problem with this one is that, see, listen to me. Let's assume, remember, where are the group members? Members here is one in here, one in here. Are you following me or not? Yes, and maybe one in here. Assume this one wants to send to this one. He is going to go through which tree? This tree. Would he go this way? Would it be better? Would it be more efficient if he goes this? It would be more efficient if he goes this way. But in this algorithm, he cannot do that. Why? Because all of them will share the what? Will share the same tree. In the PIM SIM, the one that I will show you in just, which is a protocol independent multicast sparse mode, you start with this. But discover that there is a shorter tree that is based on a source than each to the other one. See this one here? How many hops did he goes to reach R1? If R4 reaches R1, how many hops does he go through? He will go through 4 hops. He could have gone through 2 hops. Do you follow me or not? But in this protocol, he is not allowed to do that. Why? Tree. All of them will share the same tree. Clear? Okay, so one more time. May result in what? Of traffic near the core and may create suboptimum routes. Do you understand what suboptimum routes? Suboptimum routes means not the shortest distance, for example. Question? Cannot hear you. No. There is only one routing points. But the thing is that you could, all of these nodes have the capability of acting as a what? Which means what? If one of them fails, the other one is ready to what? To take over. Usually the smallest IP address is elected as a what? As a core point. Remember, when I say a router with the smallest IP address, the IP address, all of them are how many bit long? 30. So when I say smallest IP address means what? Means the entry, those numbers in the IP address are small rather than what? High. In other words, they are what? At top of a blocks rather than at what blocks. Did you get this or not? Okay, good. Now, I will show you the PIM that will switch from another tree, from a shared tree to a source-based tree in a minute. Let's go on MOSPF tree. MOSPF, one more time. MOSPF stands for what? The multicast shortest path first. Now, remove the M first. Do you remember the OSPF? What is the algorithm used in OSPF? The Dijkstra algorithm is based on the fact that every router will have a map of what? And he will choose the what? The shortest distance to each other router. Clear? The shortest distance. In the OSPF, every router will what? Will disseminate information. He will tell every other router in the network, this is the state of my links. I have 3 links. Links are what? On. They are all operational and so on and so forth. The bandwidth, delay, all of this state. In the MOSPF, to this information, they will also what? Broadcast whether there are members network or not. How do they know that? Through which protocol? How do the routers know that there are hosts which are interested in the multicast It's using the protocol that we discussed, what, which is the IGMP, the Internet Group Management Protocol. So this route he will broadcast, or will he disseminate information telling what is this G2, G3 means. Can you tell me what is G2, G3? This one is connected to a leaf network, and the leaf network, there are hosts who are interested in what? Multicast group G2 and multicast group what? G3. He will disseminate that information. He is interested in G2, this one is G1, and so on and so forth. Everyone is interested in something. Now, let's see how it works at the beginning. Let's concentrate on this current router. There is a current router interest. This is the source. At the beginning, what is he going to do? When he receives a packet, notice, by the way, the source to this. This source belongs to which group? Group number 1, G1. He will send to this guy. Clear? Let's not worry about where this goes here. Concentrate on this router. This is the current router. What does he do? He send it to here. He send it to here, here, here. Now, here, there is an interest. Are you following me or not? If you look at it, again, concentrate on the what? On the current router. Just concentrate on this router. Do not worry about it. Concentrate on this router. So at the beginning, this is the tree. But then he discovers what? Is that there is no interest in here. There is no interest in here. Now, notice, by the way, why did he choose this? Why did he choose this rather than this? If you see what is the distances? 4 plus what? Plus what? 1. That if he goes this way, it would have been what? 8. He would choose the 7. But does he know these distances? He knows from the what? From the OSPF. Because in the OSPF, every router will have a what? Did you get my point or not? Yes, remember Dijkstra? In the Dijkstra, you assume what? The map of your network. So he chose this one here. By the way, this I will give it to you in the homework and in the fine. I win here. Okay, so in this case here, they will what? He will choose this one. He will choose this one. Now, discover. What did he say? This guy here send what? He will send back a what? A prune message telling him what? In what? In here. Are you following me or not? See, when he was sending it to here, he thought that in here in G1. Is there an interest in G1? There is no interest in G1. So this is what the tree becomes like this. Did you get this or not? Now, in his table, what do you see? Well, in his multicast routing table, this is what he see. What do you see? The group, the source is S, which is this. The group is what? G1. What is the interface? It's the M2. In other words, he knows that if I receive, listen to this, if I receive packets from what? From this port, sending it to which interface? M2. I will not send it through what? M1. This is what you see in his table. What would you see in this table? Assuming that we are interested in this router right now. What would you see? You will see if I receive S, comma what? G1, then which interface am I forwarding to this interface? Clear? And you choose the what? You choose the shortest distance. The distance is what? 4 plus 2 plus 1 is shorter than what? Is shorter than, but that there is an interest in the multicast group here. Let's assume there is an interest. Would you go that way? You would go this way. Why? Because the distance is what? Is 4 to 4. Yes? But let's assume this one was what? 1, 1, 1. How would you go this way? Are you following me or not? Because the criteria is to find the what? The shortest distance for the other what? To every other router in the network. Clear? Clear? Now, the PIM. Let's look at the PIM right now. The protocol independent multicast. It does not, unlike the previous protocols, which is the what? The DB what? MOSPF. The DBMRP, again, is based on what? Flood and what? Prone. Flood and prone. Between these and the PIM is that this one does work only, routing protocol is the what? It's a distance vector. This work only if the protocol is what? Or SPF. This one here, the PIM, does underlying unicast protocol. It does not depend on the underlying unicast protocol, whether it's DB or whether what. Whether it will work either way. Clear? It will work either way. So that's why. So it does not depend on the underlying unicast routing protocol. Can be classified into the PIM-DIM, This is appropriate in an environment where the multicast group members are relatively, they are what? Clustered together. Clustered together. Those hosts that are interested in a cast group. They are densely located and the bandwidth is widely available. Bandwidth widely available. As I was showing just a second, the PIMDM is based on the what? Is base 3, which is what? Flood and prone. When you do flooding, it means that it will eat a lot of what? Now, if the what? If the all hosts which are interested in a cast group are in a dense environment means what? Clustered together. Only these branches will be handling the what? The flooding. All the others will not, because there is no just in a dense area. Clear? So if the bandwidth is available in this, the flood and prone, it's a good technique to do it. Clear? Okay. So in the PIMDM, the protocol designed to operate in an environment, the group members are relatively densely located and the bandwidth is widely available. The PIMDM, the protocol designed to operate in an environment where the multicast group members are distributed regions. Now listen to me. If they are distributed across many regions, which means widely located, does it make sense to use a source-based tree? In a sense, or it does not make sense? If they are located all over the place, in a sparse mode, remember, in a source-based, it is always based on what? Flood. And if they are located all over the place, it means you are going to flood the multicast packets over what? Branches. A large number of branches, but small number of what? Recipient. Are you losing me or not? You are losing me? The recipients are what? Large number or small number? They are located what? Not close to each other, far away from each other. Which means what? From the source-based tree, let's assume I am the source, and the destinations are located all over the place. Small. It means when I flood, my flood will go to what? A large number of branches, those sparsely located hosts. Did you get this or not? Yes? Will eat a lot of what? It's a lot of bandwidth. In this case, one more time, in this case, the host located what? Very close to each other. So when I send the flooding, it will what? It will certain set of branches that requires what? Large bandwidth. All the others are what? Are not. Clear? Okay, so the PIMDM protocol designed to operate in an environment where multicast members are distributed and the bandwidth is not necessarily what? Widely available. Is not necessarily widely available. In this case, we will see it is better to have a what? A shared tree. Why is it a shared tree? Remember, only if you are interested in receiving a multicast group, you will send a what? Message. Remember the join message? One more time. Remember, only when you are interested, you will send a join to the rendezvous point or to the core point. There is no what? Flooding involved. There is no flooding involved. Oh. Now, remember what I just told you a moment ago, as I will show you in a minute. In the PIMDM, if you that there is a better tree than a shared tree that is based on a what? You can switch from a what? From a shared tree to a what? A source-based tree. Again, I will show you that in just a second. Let's see, first of all, the PIMDM. The PIMDM, again, is based on what? On source-based tree, which means what? Flood and what? Okay, let's take this one. This is the source. Where are the groups? The groups are one in here, one in here, one in here, one in here, one in here. Are they densely located? Now, what does this one do first? He will send the packet. A copy will make to this, and this is what? The first packet is what? Broadcasted. Now, I'm using the word broadcasted, but you need to, the first packet is actually what? It's flooded. Are you following? When you say broad, I change this. What is the difference? What is the difference? In a broadcast, what is the destination address? Destination address will be what? In this case here, what is the destination address? The destination address will be the multicast group. That's what I just saw now. But the flooding means what? Means when a router receives it, he will make copies to all of its what? To all of its interfaces. Now, tell me what happened here. Tell me what from here to here. This is the second packet, is a what? Actually what? A multicast. Did this one send it? Why he did not send it to here? Why did not he send it to here? Because this one, listen to this, this one, or a pruning message, this one, did this one receive the first packet? Receives the first packet. He received the first packet, but there was no interest. There was no interest in the network. This one will send a what? A pruning message to this router. What happens? This one is no longer part. Are you following or not? It's no longer part of the tree. The tree is now like this. This. It is a source-based. Clear? Clear? Now, let's see the PIMSum so that you understand what I'm talking about. Okay, where is the rendezvous point? This, by the way, these are the groups. G1, G1, G1. Where is the rendezvous point? This is the rendezvous point. Yes? They want to, no flooding in here. They want to join. What do they send? Unicast. This is a unicast. What cast? Messages. Clear? This one will send a what? A unicast message to this. Notice this one is sending a unicast message to this one here. This router will what? Interface to be what? To be what? To be part of the tree. Are you following now? This one will send a what? Well, this one will send to this. This one will send to this. What? This is now how the tree look like. The multicast tree after the join. It would look like this. Okay, notice by the way, this is not a source. This is the rendezvous point. Everyone. So for example, if this one wants to send, assume this is a source. If he wants to send a multicast, how does it go? Follow me. This. What if this one wants to send? What does it do? This. Did you get this or not? All of them, are they sharing the same tree? They are all sharing the same tree. Now, are you following me so far or not? Now, this one decided to what? To leave. One network leaves the group G1. This one decided to leave. What will he send? He will send back to who? To the rendezvous point. Are you following or not? Yes? No, not to the source, to the rendezvous point. Okay, why is he sending it? Why is he sending it? Notice, by the way, when this pruning message to this one, when this one is sending a pruning message to this one, what will this one do? This one, remember this interface was configured to be part of the tree? It is no longer part. He removes it from his memory. And then what does he do? He forwards the pruning message to the what? And then the rendezvous point, look at it. Now, listen to me. When this one is sending this, I made a mistake here. One more time. When this one is sending the pruning message to this guy, sending this guy, this one is what? This one is this longer part of the tree. Are you following me or not? Is no longer part of the tree. But is this still part of the tree? This one is still part of the tree. An interest to what? To this one. When will this part of the tree anymore? This one, when this one send a what? A pruning message. Then this one will relay the pruning message to him. Did you get my point or not? This one will only what? Will only remove this branch in here. Now, notice why there is no what? There is no group member in here. So this one is not part of the tree. Clear? So is it still shared? It is still shared. Are you following or not? Now, let's look at another example so that you can see it. The concept of switching. Let's assume this is the rendezvous point. This is the rendezvous point. He sent, like I showed you a moment ago, he sent a join message, a unicast join message to here. This one also join message. Clear? Now listen to me. This router, this is the tree now. This router, when he receives, listen to this, careful. When this router receives multicast packets from a source in here, he knows the source IP address. He knows from where. How does this one know the source IP address of this? He knows the source IP address of this because cast packet, what goes in the source IP address? The source IP address is the host, this one. Are you following me or not? There is a what? There is a shorter path to this rather than what? Rather than this. Did you get my point or not? How? How did he discover that this is a shorter one? From the unicast. I don't care. This is independent. Are you following? From the unicast routing protocol, whatever it is, he is a shorter path to here. What does he do? Listen to what does he do. He sends the pruning message to the RP. Why? Because he is telling the RP, I don't want you to send me the what? Those multicast packets anymore. And to this, he sent a join message to this one. Did you lose me? You lost. Did you understand what I said? Oh, so what does the tree look like? Can you like this one is still what? A shared tree among what? Among verset. But this one will be what? Here. So when this one sent to this one, he will send it to what? Here. Did you get my point or not? Rather than what? Rather than going this way. Because he discovered joining via RP, the router can switch to a source-specific tree, increase performance, less constant path. Are you following or not? This one prefers to go this way rather than to go this way. Clear? But you, with what? With what a tree? You start with a what? With a shared tree. You start and then you discover, if you can discover a better source-based tree, then it's fine. You can switch on a source-based tree. Clear? Okay, good. This is, again, as I told you, this is the one that we use currently. So predominantly use currently the MOSPF and the DBS, they are what? They lost their appeal. The one that is used most often is the PIMSM. Yes. After the what? The shared tree? You need to specify which tree. After the shared tree is formed. No, after the shared tree is formed, all the multicasts will be, routers will only have in their entries like this. They don't care about what? What is the source? They don't care who the source are because they are all going to what? Share the same tree. But once you switch from this tree to this tree, you need to have in your entry a designation for the what? Because this one become a what? A source-based tree, which means what? You need to designate it like this. Do you understand what I just said or not? When you are in a shared tree, you don't care about what? Where the source is. All of them will share the same what? Will go over the same tree. You don't care about where is the source. But once you switch, then you need to what? Then you need to keep track of what? Where? Did you get my point or not? Did you get my point or not? Yes or no? Did I form a new tree what? No, my dear, I don't know when you, what tree? R3 to who? This you send a join message. Once you find this, you need to, but this one does not send you a copy. What if R3 and what? I'm not getting this. You mean at the same time that this one is, I told you that this one will send a pruning message to here. You mean before sending the pruning message? He will get two copies, one of them. He will drop one of them. What I'm trying to tell you is that when this one send a pruning, he immediately will send a what? A join message to this, so that he will receive the packets from this source through than this tree. Did you get it or not? Did you get it? Well, why is this bothering you? I'm not sure about it. R6 is the core point, is the rendezvous point. If he is interested in what? And you mean there is one in here? Then it will go this way. And the share tree is the share tree is not going anywhere. What is going to be pruned is only this branch. Do you understand? Only this branch will be pruned. In other words, if there is one is interested in here, then it will be. Do you see this or not? Only this branch is not going to be part of what? Share tree decided that he preferred to receive the multicast group through what? From the source, using a source. Clear? Okay, good. Now, one last thing about which is the following. Interdomain. This is even more complicated. First of all, what does interdomain mean? Interdomain means what? A multicast between autonomous systems. Is it possible that some which are interested in receiving the some destination hosts which are interested in receiving multicast packets, traffic, are located in a different autonomous system, in a different so that you understand what I'm talking about. Is this an autonomous system? Autonomous system, autonomous system, autonomous system. Is it possible that a source in here, in this autonomous, and there are what? There are some group members in this autonomous system? This is what is known as what? Interdomain. Interdomain means what? Means the group members are not located within the domain. This becomes a little bit more what? More complicated. Why is it a little bit more complicated? Because it's on what? Its own policy. By the way, how would this one know that there is a source here? How would this one here know that there is a source in here? This one is not going, by the way, will a flood, tell me, will a flooding works in this situation? Flooding will not work in this situation. You are not going to what? Multicast packets to what? To all autonomous systems. So it becomes much more complicated. See what are the efforts that is being done here. The three ones that are most widely used, the M-bone. M-bone, it looks like a what? Looks like a food for dogs. M-bone. M-bone stands for what? Backbone. Multicast backbone, which I'll explain to you in just a second. The other one is MSDP. MSDP stands for Multicast Discovery Protocol. Multicast Source Discovery Protocol. And the third one, you can tell what is the third one. Third one is an PGP. PGP stands for what? The Border Gateway Protocol. This, the multicast or the multi-protocol Border Gateway Protocol. Extension of that. Clear? Clear? Remember, in PGP, every PGP router, what is he going to advertise to the or to his peers? His peers means what? The PGP routers in a different autonomous system. In a different autonomous system. We study in PGP, he will advertise paths. He will not advertise what? Advertise distances. He will only advertise what? Paths. In this case here, what will he also advertise? Multicast groups. Multicast groups, sources of multicast groups. He will advertise it to his peers as well. Clear? He doesn't tell them where it is located, but he just tells them what? There is a group going on in this, in my autonomous system. Would you like to join? Clear? Okay, we'll see that in just a start. First of all, with the M-bone. The M-bone is the earliest protocol. In other words, this is how it started. What is an M-bone? M-bone is a virtual network. That is what? That is what? Overlaid the internet. Do you follow me? We have the internet. We have the internet, and over on top of it, we have a network of what? Multicast. What? A multicast backbone. This multicast backbone consists of separate islands. This is an island. All of them support multicast protocols. However, they cannot reach each other. They are not connected to each other. Did you get my point or not? They're connected to each other. But they can be connected through who? Through the internet. Or not? No, you didn't. Let me show it to you graphically. This island. This is another island. This is a third island. What is this? That's the internet. This is a what? Bone. Island. Listen to me. Is it possible that they are connected like this? It is possible that this island is connected to this. You follow me or not? Okay, but they are not connected to this island. Yes? But could they go through the internet? Could go through the internet. What is the problem? The problem is that the internet here, the routers, do not support what? Multicast. Do not support multicast. But all of these islands do support multicast. They do support multicast. They do have the multicast routing protocol implemented in them. So what do they do? What do they do? These networks, these islands, are connected across the internet between each other, I mean from this one to this one, via a point to point. I need you to understand what point to point means. Point to point tunnel. What is a tunnel? Did we talk about tunneling before? In general, what is tunneling? Tunneling is the process when you want to send a protocol or when packets using a certain protocol over a network that does not support this protocol, or does not support multicasting. So what do? They create a tunnel to point tunnel. Question: inside this tunnel, could there be multiple routers? Inside this tunnel, could there be multiple routers? But to them, it looks like a what? A point to point. The islands, they look like a what? In other words, look at it this way. Another router this, another router this, another router this, and then this. Yes? Is it possible that it goes through multiple routers before it reaches this? Yes or no? But to them, it's a point-to-point tunnel. Are you following one? Now, will those see the multicast? No. So, multicast packet. They take the multicast packet and they encapsulate it into what? Into a regular IP packet. Are you following me or not? Who is creating the multicast? Sorry, I said who is creating the mistake. Who is creating the tunnel? The router in here and the router in are they both multicast ready? When I say do they understand multicast? They do understand multicast. They put the multicast packet inside a IP packet. Yes? In the IP packet, in the outer packet, what is the source? What is the source IP address? In the outside IP address will be what? Will be the IP address of this router. Destination IP address will be of this router. In the header of the packet, there is a what? There is a field called what? Protocol, which identify what is being encapsulated inside that packet. They use the number what? 4 means what? What is being encapsulated is a what? A multicast. Will this one see the multicast or they will not? Here, the routers in here. Will they see the multicast? They will not just see the regular what? They will just see the regular IP packets. When it reaches to this router see that the encapsulated is a multicast. What does he do? He removes the what? The outer. What remains? The multicast packet. This island support multicasting. It will be the group members in here. Did you get my point or not? Yes or no? Tunneling, by the way, is over the place. The concept of tunneling. So far, we have seen it in what? We have seen it in mobile IPs. In multicasting. In a minute, we will see it in what? IP version. Are you following me or not? We will see it in IP version 6 in a minute. Did you get my point? Okay. So this one tunnel. So the tunnels allow IP multicast traffic to pass through non-mobile routers. Allow the traffic to pass through non-multicast capable routers. Multicast packets are inside IP packets. The encapsulation is added at the ingress. What does ingress mean? The input of a tunnel at where? At the egress of the tunnel. At the egress of the tunnel means what? At the output of the clear? Clear? Okay. And did you understand what do I mean by the M-bone network? Is this one network? This one and this one and this one. Are they one network or they are? They are islands of networks, but because they can communicate with each other, are they connected to each other? This one and this one. Are they connected to each other? They are not connected to each other. They are connected to the what? To the regular. So that's why we call them what? A virtual network. A virtual network that is overlaid the internet. Clear? Oh, this one, by the way, is still you. What I'm saying is that this was the first solution for providing multicasting across what? Across this and this. Are they different autonomous systems? They are different autonomous systems, but they what? Multicasting. They both support multicast. Now, if we go from here to here, do you need a tunnel? Need a tunnel. Why? Because this one and this one are what? Are both multicast ready. Clear? But not like this. Generally, they are connected to the what? To the internet, which means what? Tunnels will be established. Clear? Okay. And one more time, before I leave this. Do you understand when I say a tunnel in a point-to-point? There might be what? Multiple routers along the way. But to this, it looks like you are passing a what? A tunnel to the other side. Did you get this or not? It looks like you are passing through a tunnel to the other side. Oh, the next one. Eh? This is, again, by the way, this is the M-bone tunnel. What do you see in here? What do you see in here? This is the inner packet. What do you see? The source IP address. What is the destination? The group. No, the group. This is the inner packet. The source IP address. What is this? It's the group address. And then in the outer packet, what do you see? You see R1 and what? Tunnel is created here. Did you get this or not? Okay, again, inside this tunnel, can we here? Can we have multiple routers? We can have multiple routers. Are you following me or not? Now, when this one goes through multiple routers, will this one change or will only the frame change? You lost me here. Did you lose me? You lost me. This R1 and R2, then it goes through multiple routers? When it goes through the multiple routers, will this one change? In other words, will they change R1 and R2 or they will not change it? So what will change? I keep repeating and you are not listening to my question. Multiple routers in this, in here, inside the tunnel. Could there be multiple routers? This packet, R1, through multiple routers across the internet. Will this packet change? When you send about multicasting, when you send a packet across the internet, will the source and destination, why would it change here? This one also will not change. So when you go in here, another router to a third router, what is going to change? Goodness heaven, jeez, we are in the advanced class and I still need to explain to them to change when the packet goes. Oh my goodness heaven, jeez, I'm so depressed here. Please listen to my question. Forget about multicasting. Forget about multicasting. When across the internet, does it go through one router or multiple routers? Multiple routers. I'm sending a packet. What is this? My IP address. What is the destination IP address? Yours. Yes? As that packet with the routers in the internet, will the packet change? Will the IP address change? What will change? The packet here. It's the same thing. It's the same thing. This is a regular packet. Regular packet. Is this a multicast or a unicast? This is a unicast. And what? R2. So when it goes through multiple routers, which does not support what? Does not support multicast, this is behaved just like any other router. Yes or no? Will R1 and R2 change? What will change? The addresses of the what? Of the frame will change. Not of the packet. Of the packet doesn't change. So receive this. When this one receives this, he sees his destination address. Yes? He fulfilled that what is being encapsulated is a what? It's a multicast. What does he do? Outer header. Yes? What remains? The multicast. This network, this island, it's a what? It's a multicast ready. You follow me or not? He can send the multicast over this. Clear. Tell me what is this? This is 450, guys. Through the internet, the IP addresses are not going to change. Are not going to change. What is going to change is the MAC addresses. The IP addresses is always the ultimate source and the what? Who is the ultimate source here? R1. Who is the ultimate destination? R2. It's not the source of the what? Whoever is establishing the tunnel. Clear? Okay. Next one is MSDP. MSDP stands for what? The Source Discovery Protocol. Is a protocol used to tie PIMSIM to different autonomous systems. What does this mean? There is a PIMSIM tree. Remember, a PIMSIM tree. So there is a shared tree in one autonomous system, another shared tree in a different autonomous system, a third shared autonomous system. Now, what does that mean? It means autonomous system, there's a what? There's a core point, a rendezvous point. This one attempt to connect those core points. Attempt to connect those what? Core points, which means what? Attempt to connect those shared. MSDP is a protocol used to tie the PIMSIM trees in different autonomous systems or different domains. RP stands for what? The rendezvous point. in a PIMSM domain knows about all active source its domain. Tell me, how does it know? Did you understand the second bullet? Did you understand the second? In a single domain, does the RP stands for what? Rendezvous point, the core point. Does he know all the what? Does he know all the sources? Domain, in that domain. Does he know all the group members? How? They join the remember the PIMSM? Do they send join message? So he knows all the what? He knows all the what? All the active domain. Every RP, every rendezvous point is paired. What is the meaning of the word? Equal. Is paired with other rendezvous points in different what? Domain. Using what? MSDP. Using this protocol, MSDP. Which means is this a rendezvous point? Is this a rendezvous point? In a different domain. Is this in a different domain? But they are what? They are other. Did you get this or not? Through what? MSDP. So source registers. When a source registers with the RP in its domain, when you send a join register with the rendezvous point, that RP will convey this information using MSDP source active message to the peers. Are you following me or not? What does that mean? This RP will what? Will tell this guy, who registered with me. This one is telling this one. This one is telling this one. By the way, will he tell this one? Not according to this diagram. Why? And according to this, only connected with this and it's connected with this. Clear? Okay. Let's concentrate on this. The source is registering. He is joining. Yes? He is joining. This is, let's look at it. This, what is the first step? What is the first step? A source joins the rendezvous domain in this domain. What is this going to do? He will send it to here. He will send it to, you follow me or not? What will this one do? He will send it to here. This one will send it to here. Will send it to here. Yes? Who is this? This is a what? A router. Are you following me? This is to a what? In other words, this sender, this is the receiver. I said this is a router. I'm sorry. This is a receiver. Receiver is interested in receiving the what? The multicast. So when he joins with what? Rendezvous point. When he joins with this rendezvous point, he is going to receive what? All of this multicast from here. Okay. So the SA message. SA means active. Source active means what? This one is telling his peers, I have a source in my domain. Active. Active means what? He is involved in a what? He is involved in a multicast group. In a group. So source active. S, G. S, G. What else does he need to tell them? What does he need to tell them? The IP address of the rendezvous point part what? A. Which means what is he telling them? What is he telling them? What is this one and this one? What is this one is telling this one and this one? He is telling them, if you want to receive this multicast group, you let me know because you register with me. You need to join. Is a join a multicast? Sorry. Is a join message a unicast? The join. Is it a unicast? It is a unicast. To who? Now, to who? To this rendezvous point. Know the address of this. He needs to tell them. How does this one know the address of this rendezvous point? I'm not sure. Did you get my point? Did you get my point or not? How does this one know the address of the rendezvous point? He is telling them, look what he is telling them. He is telling them, I have a source that is active in my network. My IP address, if you want to join, this is my IP address. When this one, by the way, when this one is just a matter of relay. Are you following me? Just a matter of relay. In other words, when this one wants to join, he still needs to a unicast message to what? To this rendezvous. It might go this way, but the ultimate destination is what? Is RPN. Clear? Clear? Okay, so this one here is going to send it to all. And then what happens in step, tell me what is happening in step 3. This one is sending the what? The join message. Join message. Clear? Join message. To which? What are they joining? They are joining this group, which is what? SG. So look at this here, by the way, here, and then what? So where is the tree? Can you show me where is the tree? Look at my finger. Did you get it or not? Yes or no? Are these in bold? No. No receivers in here. The receiver was only in. Clear? Okay, good. Do you understand why do they? The source discovery, you are trying to discover where is the what? Source of the multicast. Where is the source of the multicast? Rendezvous point will tell you. Clear? And finally, the last one is the MPGP. Again, as I told you, this is an extension of PGP. It's struggling. This protocol is really struggling. And the reason that's struggling because PGP is a what? Is a very complicated protocol. More what? More complications into it. Okay, and not all autonomous systems support what? Multiplayer. Okay, so MPGP is an extension of PGP. Provides two paths between autonomous systems. One for what? Multicasting. Which means what? When he advertises to his peer PGPs, he will advertise what? Two tables, two path vector. What? For the unicast, and one of them is a what? Is for the multicast. Clear? And MPGP is a shared group multicast protocol in which one node in the autonomous system acts as a rendezvous point. So it's also based on what? Based on the shared tree, based on the PIM-SIM. Clear? Internally. Internally, he needs to what? He needs to advertise that based on what? Based on PGP messages. Clear? Oh, this is, it took us I thought I can finish it in 2 lectures. It took us 3 lectures by casting. But did you get a general idea? Okay, now when you take, if you take CS1, anybody taking CS551? Or is it planning to take CS551? You will see they will cover this. But I don't think they will cover it in the same detail that I did. Papers, and they will tell you to what? Read papers. Now, I will be posting this weekend a tutorial paper, very straightforward, describing all of these protocols that I just did for you. Clear? Describing it with examples. Clear? Okay, good. Now, let's continue with our discussion. Next, what do I want to introduce you? Now, you might be introducing us to what? To the next generation IP, which is called what? IP version 6. Notice by the next generation, the first name of IP, what? IPNG. NG stands for what? Next generation. When did they develop it? Listen, developed it in the mid-80s, which means we are talking about what? 2020. You follow me or not? Why? Why did they start talking about IP version 6? They realized that run out of what? IP addresses. They are going to run out. How long is the IP at? 23, oops, 32. I read it backwards. 32-bit address. How many IP addresses are there? Version 4. 2 to the 32. Why do I say theoretically? Some of them are reserved, and there is a lot of what? Waste. Remember IP addressing. The classical IP addressing, there was a lot of waste. So they started working on what? But in the meantime, they came up with temporary solutions to prevent running out of what? IP version 4 until they finalize this. Now, those temporary solutions proved to be more appealing than deploying this. Did you understand that or not? What are these temporary solutions? The first temporary solution, which we is decider. Decider, which stands for what? The classless interdomain routing. Reduction of the waste of the IP addresses, because I'm not classes anymore. I will give you what? Blocks. In addition, what did decider prevent? What did it allow? It allowed aggregation of the address, reducing the size of what? The routing tables. Do you remember the aggregation? Do you remember how it aggregated IP addresses? It resulted in what? Reduction of the routing tables. Clear entry. That's the first temporary solution. What is the next one? The next one is, which is the what? Which is the network address translators that allow what? Allow hosts to use what? IP addresses in their private network and share public IP address on the outside world. Did you get this or not? Now, if you remember from 450, how many of you took 450? If you remember from 450, we have what is known as a NAT slash what? PAT, port address translator, and network address translator. It allows multiple hosts to share the same public IP address. Yes? Those two solutions prove effective in what? Slowing down the time that they were print of what? IP version 4 addresses. Clear? Only temporary solution. They wanted what? They wanted a long-term solution. And started developing IP version 6. They said, let's not only solve the problem of the IP version 4, let's see if we can the functionality of the IP itself. For example, introduce what? Introduce support to mobility, and so on and so forth. Now listen to this. While they were working on this, other protocols were developed to support these as an addition to IP. But one of them we already talked about, which is what? The mobile IP. Remember the mobile IP? That was developed in IP. It's not part of IP version 6. And the other protocol, which we will discuss in the, they call it what? IPsec. IPsec means what? IP security, which is what? Developed to provide something to the IP version 4. Clear? Clear? You have to understand, before we go into the details, you have to understand one thing, is that when you develop a new protocol, you have to understand that you cannot deploy it what? Deploy it all over the place overnight. Actually, the first is, it's a joke, but it's really, it's not a joke. They said, how are we going to deploy IP version 6? One of the participants in the IETF Engineering Task Force, they say, let's designate one day, a flag day. They call it a flag day, where all devices stops work. In other words, you stop using your computer. You stop working. Everybody. They call a flag day means like a holiday. Think about it this way. We're going to what? Deploy IP version 6 in the entire internet. Did you get this? Did some analysis, first of all, whether this is feasible or not? No way it is feasible. Follow me or not? They need to bring what? Who is going to configure them? Administrators. You agree? They are not going to configure themselves. Routers are not going to configure themselves with IP version 6. You need to what? To configure them. They said we need to bring what? Millions of administrators along across the globe to what? To update their routers with IP version 6. Clear the work. People would like to have this because then they will take one day off. Joke. Okay, good. Thank you. Okay, so let's see now if you understand the motivation. Well, the 32-bit address is soon to be what? Completely what? Allocated. By the way, they are going to run out of IP addresses around 2011, which means what? Are you following me or not? But there are still some what? There are still some left. One more time, why did they version 4 addresses? They ran out of IP version 4 addresses because when they developed IP version 4, there was no all of these gadgets, your cell phones, smartphones, the tablets, all IP pad, all of these things, all of these internet-ready devices in the kitchen, a toaster, a refrigerator, air conditioner, or whatever, all of these devices. Look at these devices. All of them require what? IP addresses. This is, what is this? A refrigerator? This is a refrigerator. This is a computer, a mobile phone. This is like a tablet or something. This is a keyboard. What are these devices? By the way, what is this? A gas station, a gas pump. You follow me on the address for a gas pump. Did you get my point or not? So it's just, they said what? They said, let's develop this IP version 6. And again, as I told you, they moved the performance. They said, as long as we are going to change the IP address, we might as well do some other stuff. One of the other, let's see if you can help me here. Let's see if you can help to look at the IP version 4 and the IP version 6 headers. First of all, what is the IP? The cleaner charts, this is from the next session. Sorry, the afternoon. Okay, concentrate. Constantly. How long is the IP version 6? Look at how long it is. 128 bits. 28 bits, which means how many IP version 6 addresses do we have? We have this number. Let me show it to you. Get amused a little bit. One second. Okay. This total. Do you see this? This is the total number of what? It's 3.4 times 38. If you open it, it's like this. This is how many IP version 6 addresses are. They calculated, listen to this, every square foot, every square feet, which is just a brick, just a small brick, like this one. It's 1 feet by 1 feet, roughly. They said every square foot of the globe will have 1,500 addresses allocated to it. 1,500 for every what? Square foot. You follow me or not? They're going to run out of this in our lifetime. After we die, who cares? After you die, you die. Who cares? Let them. I'm not sure you are getting my point. Okay. What other? A couple of other things before next time I run out of time here. Let me show you another thing here. Remember IP version 6, the header? The header is anywhere between 20 bytes to what? 60 bytes. IP version 6, this is a what? A fixed header. A fixed header. Yes? Cannot hear you. What is another checksum? Do you remember the header checksum? In the header of what? IP version 4. IP version 6, we have error detection in the frame layer, in the MAC layer, and we have in the what? In the TCP layer, and in the UDP, in the transport layer protocol. What do we need another layer for? So they removed it. They removed it. There is no checking of errors in what? In IP version 6. Makes it faster or slower? It makes it a little bit faster. Did you understand that or not? Remember fragmentation. In fragmentation in IP version 4, both the source and the routers are allowed. In here, only the source is allowed to fragment. Routers are not allowed to what? To fragment. There is no. Did you get this or not? Okay. But I will show you this scenario. Did I run out of time? Yeah. Okay. I will show it to you next time. Clear? Okay.